Hi everyone, this is Kyung Kim from Seoul National University in Korea. It is my great pleasure to meet you in IABSE webinar series today. And today I would like to talk about the probabilistic stability evaluation of vehicles under strong winds for bridge traffic control. And this is one of the research product we recently developed with cooperation with bridge owners in Korea. Let me start with a brief introduction of myself. I'm fellow members of IABSE and currently serve as the chair of Korean group of IABSE. And also I'm director of Korea Bridge Design and Engineering Research Center in Seoul National University. Wind-induced vehicle accidents on long-span bridge were identified, observed in many countries. A couple of years ago, the Typhoon Jebi struck Japan and rollover accidents were observed at the time. The same rollover accidents were also observed in Korea. So the left-hand side, you can see a couple of accidents with the 1 hour interval at the almost same place along the bridge. Last year, many typhoons struck Korea, and July, due to the Typhoon Doners, GWANGAN Bridge was temporarily closed. And September, Typhoon Ringling invaded Korean Peninsula, and the western side coastal area was, there was many long-span bridges, and the bridge was closed, and the bridge were closed and reopened as the typhoon moves up to the north side. Also, same September, we had another Typhoon Tapa on the southern and eastern area of the Korean Peninsula. And 10 days later, we have one more Typhoon Mita, and Ulsan Bridge was temporarily closed at the time. So this photo shows us the overall layout of the GWANGAN Bridge. That is one of the examined bridge today. And as I mentioned before, there was 2 consecutive rollover accidents with 1 hour interval. But the interesting point was that the accident was observed in approaching spans, not the main span. Also, the accident event were observed in lower deck, not upper deck. So that was our motivation of this research, and we would like to provide some framework of vulnerability assessment of vehicles under strong winds. We implemented 3 research items inside. The first one is wind tunnel test for measuring aerodynamic coefficients. And the second was determine critical wind speed via vehicle simulations. And we would like to obtain this kind of critical wind speed curves for each wind direction. For examples, this specific case, you can see the vehicle is most vulnerable to the wind direction from west directions, and then the critical wind speed will be around 18 meters per second. And by this way, we can obtain wind speed for traffic controls based on this critical wind speed curve. And then the last item is wind environmental analysis. So we obtain the long-term wind speed data and also develop some long-term probability distribution functions. And by combining this information with critical wind speed curve, and we can determine a vulnerability index and subscript E, which is expected time of incidence of critical wind speed per year. So that is sort of risk index. So the GWANGAN bridge provides total 8 traffic lanes, 4 traffics on the upper deck for the western bound traffic, and 4 lanes on the lower deck for eastern bound traffic. As you can see here, the approaching spans girder is without truss member, and the main spans equipped with truss members between upper deck and lower deck. So for the wind tunnel test, we developed 2 different section models. So let me talk about the step 1, wind tunnel test to measure the aerodynamic coefficient of the vehicle. We developed new GX system, so we can rotate the cross section of the bridge deck to control the incident angles. And by installing small load cells inside the vehicle models, we can measure the aerodynamic loads, 3 forces and 3 moments. And then by changing the incident angles, we can develop this kind of aerodynamic coefficients for these specific bridges. So this shows us the experimental results of the aerodynamic force of approaching spans, the vehicles on approaching spans. So for the upper deck, please note that the dotted line here, that is the aerodynamic coefficients for the flat ground condition. So for the upper deck, you can see side force and rolling moment. The level of the aerodynamic force is almost similar to the flat ground condition. How about the low deck? The low deck is somehow different. The aerodynamic force coefficient somehow increased due to the tunneling effect between the gap, small gap between the upper deck and low decks. We also tried to measure the increased wind speed between upper deck and lower deck by the hot wire anemometers in wind tunnel test. And the vertical line denotes the undisturbed wind speed. And you can see here on the lower deck, most of the lane, the wind speed was somehow increased. And we also performed the experiment for the main spans, and you can see the truss members somehow equipped between upper deck and lower deck. So for the upper deck, the approaching span and main span provides almost similar aerodynamic coefficient, but the lower deck, you can see here, main span, the aerodynamic force was pretty much reduced due to the sheltering effect by truss members. With this measured aerodynamic coefficients, now we can estimate critical wind speed. So we consider two cases of accident. One is overturning, and the other one is side slip. So overturning is assumed when one of contact force on a wheel becomes zero. And side slip is assumed when one of vehicle axles reaches the friction limit. So what we need is tire reaction force to check this accident. So what we need is vehicle dynamics model, and you consider the first model as quasi-static vehicle model. And this model, we can calculate the tire reaction force from the equilibrium equations as shown here, combined with geometrical constraint. And the other option for the vehicle dynamics is simulation using TRUCKSM. So TRUCKSM is one of the commercial softwares which deals with vehicle dynamics. And by combining with the MATLAB SIVULINK, we can develop the vehicle motions with these proposed procedures. So for the considering the random properties of the wind velocity fluctuations, we developed 100 turbulence time histories for each wind speed, and we feed into the TRUCKSM analysis, and then TRUCKSM analysis provide us the vehicle motions according to the turbulent wind. And then we check the bridge vehicle accident, and eventually we can develop this kind of fragility curve for travel time t. And we can get 100 samples by varying a random seed of the wind velocity fluctuation. This cumulative distribution function should be developed for 16 directions and 8 traffic lanes. Okay, so this figure shows us one case, and then if we develop this kind of fragility curve for vehicle accident, and then we have to determine traffic control wind speed. For this case, what we need is the definition of the non-exceeding probability to find out traffic control wind speed, and we just apply 5% in our case. And in case, for this specific case, the determined traffic control wind speed will be 22 meter per second. So with these procedures, we can develop critical wind speed curves for each wind directions. So we vary wind directions and repeat these procedures and check the plot the traffic control wind speed, and eventually we can develop these 4 curves for each range of the bridge. And as you can see here, the wind speed for traffic control will be 14 meter per second for this specific location along the bridge. In our analysis, we examined 3 types of vehicles from sedan to tractor trailer. So by assuming the vehicle speed is fixed 80 kilometers per hour, we developed the traffic control wind speed. So the most vulnerable location will be low deck in approaching spans, and you can see here low deck truck. The traffic control wind speed should be 50 meter per second to avoid the accident, and tractor trailer is 16 meter per second. So by reducing vehicle speed to 40 kilometers per hour, we can increase the traffic control wind speed by 2 meters per second in road deck of the approaching stance. So that means the limit vehicle speed is somehow helpful to reduce the vehicle accident. So eventually, we propose traffic control protocols for the Gwanggan Bridge operators as shown here. So we start level 1 from the wind speed 15 meters per second, and we recommend a speed limit of 40 kilometers per hour. And level 2 starts from the 17 meters per second in terms of the 10-minute average wind speed. And for this case, close low deck to high side vehicles. And then level 3 starts from the 20 meters per second wind speed and close both lanes to high-sided vehicles. And from level 4 over 20 meters per second, close all lanes of the bridges. What is the definition of a high-sided vehicle? You can refer to the Humber Bridge case. So Humber bridges, they designate high-sided vehicles as shown here. So after the determining of the traffic control wind speed, we can proceed to the estimation of vulnerability index by the risk analysis. So long-term wind speed data was available, and with this wind loss plot, we can find dominant wind direction is almost parallel to the bridges. And we can develop the probability distribution function for wind speed. Based on the probability density function of wind speed for each wind directions and combining those information with fragility curve for each wind directions, we can develop the probability of exceeding critical levels during 10 minutes by taking all wind directions into consideration. Eventually, we can develop the vulnerability index and subscript E, which is defined as the expected number of accidents of critical level in 10 minutes for 1 year. That is a kind of risk index. We applied this risk index for the upper deck of the Gwanggan Bridge, and the approaching stance, the outside lane was most vulnerable, and the vulnerability index reaches around 2. That means maximum 2 rollover accident per year, okay, on upper deck. And how about lower deck? Lower deck, the vulnerability index pretty much increased than the upper deck, and the vulnerability index reaches around 15. That is the maximum 15 events per year. So if we reduce the vehicle speed, we can decrease the vulnerability index. But if you would like to keep the vehicle speed to maximum speed, 80 kilometers per hour, then the other option, another option will be installing windscreen on only covered sections this way. So we perform internal tests again to measure the changed aerodynamic forces on the vehicles, and then we evaluate vulnerability index with the windscreen again, and we realize that around 85% risk index can be reduced by installing the windscreen for the approaching span. While we are talking with the bridge operator, what they actually need was the prediction of wind speed 1 hour or 2 hours later to prepare the closing the over bridges or reopening the bridges after typhoon. So we tried to develop this kind of deep learning based wind speed prediction algorithms and training these models with past typhoon data. We somehow simulate 1 hour or 6 hour prediction in advance over the bridge. So this is very important information, and once we can provide this kind of tools, then bridge operator can spread some information related to the driving speed or driving range through the variable message signs of the bridge. And in future, autonomous vehicle should be more popular, and then this kind of information guides the vehicles with more safer driving. So you can find more detailed information in these open access articles, and I would like to thank to Busan Infrastructure Corporation for our partner, and also thank you for your kind attention of this webinar seminar. Thank you very much.